In our last video, we talked about the equivalence of the system of linear equations with the vector equation, where the coefficients in front of the linear equation variables, like x1 here, corresponds to the vector in front of x1. The coefficients of x2 then to -5 is the vector in front of the x2. We said that these two had the same solutions for x1, x2, and x3. In this video, we're going to look at the matrix equation and see that it also, according to this theorem, has the same solutions as the vector equation, which has the same solution as the system of linear equations. That's this theorem here. We are going to start by looking at the matrix equation, which is the matrix A times a vector x equals a vector b. We'll define how to do the calculation, as well as that theorem I had shown on the previous slide that shows that the linear equation has the same solution as the vector equation, which has the same solution as the corresponding matrix equation. We will continue by looking at the existence of solution for ax equals b, which says these four statements are equivalent, that the equation axb has solution for every b in Rm. If b and Rm is a linear combination of the columns of A, and that's if the columns of A span Rm, that is because every b has a solution, and last, A has a pivot position in every row. We will also look at computing ax in a different way other than this formula here, which shows us ax in terms of the vector equation. We'll just show a method of computing ax which is akin to matrix multiplication. And finally, we will look at properties of the matrix vector product A times x. The first thing we're going to do is see how to calculate this matrix A times a vector x. That's the left-hand side of the matrix equation. So if A is an m by n matrix, that's m rows. That means this each vector here, a1, a2, and an, has m elements going down. And then by n, that's the number of columns. So the number of columns equals the number of column vectors, a1, a2, up to an. So we have our matrix, and then we have x is in Rn. Then the product of A and x, denoted ax, is the linear combination of columns of A using the corresponding entries in x as weights. That is, our matrix A times x, we write A as our column vectors times our x is a1 times x1, our vector a2 times x2 up to an times xn. And I've written it here out as a linear combination or as the linear equation. And you want to note that ax is defined only if the number of columns of A equals the number of entries in x. And we'll kind of take a quick look at that at the end of this slide. So we have two examples. So here is 1a, and here's the vector x. So the way we compute this is we take the first column, multiply it times the first element of x. We take the second column, multiply it by the second element of x, and then we take the third column and multiply by the third element of x. So here's our linear combination, our vector equation, and then we can just multiply out, do our scalar times our vector to get 4, 0, 6 minus 15, and minus 7 and 21, and then we do our vector addition to get 4 plus 6 minus 7 is 3, 0 minus 15 plus 21 is 6. Our second example is we have the matrix 2, 8, -5, -3, 0, 2, and we multiply it times the vector 4x. So we take the first vector, the 2, 8, -5, and multiply it times the first coordinate of our vector. So that's times 4. Our second vector, which is -3, 0, 2, multiplied times the second coordinate, which is 7. So again, doing our vector scalar multiplication, 4 times 2 is 8, 4 times 8 is 32, 4 times -5 is -20, 7 times -3 is -21, 7 times 0 is 0, 7 times 2 is 14. Then we do our vector addition, 8 plus 21 is -13, 32 plus 0 is 32, and -20 plus 14 is -6. And last, notice that these two matrix times vectors has the number of columns of A equals the number of entries in X, right? So there's 3 columns and there are 3 entries in X. Here there are 2 columns and 2 entries in X because you want to be able to multiply, the pair off the columns with the entries in X. So if there's this extra entry here or an extra row here or extra column here, sorry, the definition wouldn't work well. So that's what it means by you have to have the number of columns equal the number of entries. Our next equation for V1, V2, and V3 in Rm, write 3v1 minus 5v2 plus 7v3 as a matrix times a vector. So here we have the vector form, or the linear combination of vectors. We want to write this as a matrix times a vector. According to our definition over here of matrix times a vector, so the coefficients is going to become our vector x. This would be the 3 minus 5 and the 7, whereas these vectors are going to become the column vectors of our matrix. So I've written this out. We have our column vectors now being v1, v2, v3, and then our 3, -5, and 7 will become our x vector because those are the things that multiply by our vectors. And so this is it. This is our matrix times our vector. Now that we've looked at how to multiply a matrix times a vector, we have this theorem here that essentially says that there's an equivalence between a system of linear equations, the corresponding vector equation, and the corresponding matrix equation. So we'll look at this theorem now and along with this example. So if A is an M by N matrix, that's M rows, N columns, with columns A1, A2 up to AN, column vectors A1, A2, AN, and if B is an Rm, the matrix equation AX equals B has the same solution as the vector equation x1a1 plus x2a2 up to xn an equals b, which in turn has the same solution of the system of linear equations represented by the augmented matrix a1, a2 up to an, and b. Relating this theorem now to this example here, we started with a set of linear equations and we came up with the augmented matrix. We just took the coefficients of the first row, 1, 2, minus 1, and 4, to make the first row of our augmented matrix. Then we took the coefficients of the second row, 0, minus 5, 3, 1, to make the coefficients, we put them on the second row of our matrix. And remember when we finally solved the matrix and it was an echelon form, we said this first row, these coefficients were associated with x1, right? The 1 and the 0. The second row was associated with coefficients 2 and minus 5. This third row was associated with the coefficients with x3. So to get the corresponding vector equation, we take the coefficients of x1, which is 1, 0, and multiply by x1. We take the coefficients associated with x2, that's 2, minus 5, and multiply by x2, and then we take the coefficients -1, 3, and multiply by x3, and that will equal to 4, 1. And this theorem here says this matrix, the solutions to the system of linear equations represented by this augmented matrix is the same set of solutions as this vector equation. Furthermore now, if we write the matrix equation, which over here, we take the vectors a1, a2, and an to make a matrix, and then we take the weights, the coefficients, the scalar coefficients to make the vector. So we'll take x1, x2, x3. That will be our vector, and then we take these column vectors to make the matrix 1, 0, 2, minus 5, 1, minus 3, and then we set it equal to 4, 1. That's our matrix equation, and this matrix equation will have the same set of solutions as this vector equation, which has the same set of solutions as the augmented matrix representing the system of equations. This theorem here, the equivalence of the three, is crucial in linear algebra because each of these come up in their own right for different kinds of questions, different type of applications. And then you can do the calculations to solve for x1, x2, x3, or answer the question. But which of these three forms you choose will depend on the question that's being asked or the question you are working on. Now that we've talked about the equivalence of the system of linear equations, vector equation, and matrix equation, we can ask when does a solution exist to our problem? And we'll look at first the matrix equation AXB has a solution if and only if B is a linear combination of the columns of A. We'll start with the example where A is equal to 1 minus 4 minus 3, 3, 2, negative 2, 4 minus 6 minus 7, and B is equal to B1, B2, B3. And the question is the equation AX equals B consistent for all B in R3? In other words, when does AX equal B have a solution? To solve this, I'm going to convert my matrix equation into the equivalent augmented matrix. So I have my 1 minus 4 minus 3, 3, 2 minus 2, 4 minus 6, 7, B1, B2, B3. You can see I do my row reduction until finally I get to 1, 0, 0, 3 minus 14, 0, 4, 10, 0, B1, B2 plus 0, B1, minus 2, B1 plus B2, minus 2, B3. And I can continue to go from this echelon form to a row-reduced echelon form, but I have enough information here from this last line. In particular, this last line, again, this row represents x1, this is x2, x3, but 0 multiplies x1, x2, x3. So this last line tells me that 0 is equal to minus 2b1 plus b2 minus 2b3. So in other words, for this system of equations to have solution, this relation must hold. 0 equals minus 2b1 plus b2 minus 2b3. So this system of equations is not consistent for every b. It is only consistent if b2 equals minus 2b1 plus 2b3. And I've written that here, the matrix equation, 1 minus 4 minus 3, 3, 2 minus 2, 4 minus 6, 7, x1, x2, x3 equals b1, b2, b3, only has solution if b2 equals 2b1 plus 2b3. So this is my final answer to this question, but I am going to do one other related problem. Let's just say we can find a b2, or we can find b1, b2, b3 such that this condition is true. Then let's write our b as a linear combination of our vectors in A. So the same problem, I kind of cleared out some space here, but I left the augmented matrix, the row reduction, that allowed us to get the fact that this has solution when b2 equals 2b1 plus 2b3. And now I'm going to look at a b that satisfies this condition. In other words, I decided to let b1 equal 1 and b2 equals b3 equals 1 because those are easy numbers, and that would tell me that b2 must equal to 4. So I'm going to look at b equals 1, 4, 1, and I'm going to see if I can write b as a linear combination of the row vectors of A. And we know how to do that. If we want to write b as a linear combination of the of the column vectors of A, I'm sorry, I think I said row, but I meant the column vectors of A, that's equivalent, that's this vector equation here. We want B to be a linear combination of the row vectors. And what we can solve that then by solving the corresponding system of linear equations using the augmented matrix. We have the augmented matrix right here. We just need to plug in b1, b2, b3 equals 1, 4, 1. And then we did the row reduction already. So I have that row reduction 1, 0, 0, 3, 14, 0, 4, 10, 0. And then b1 is equal to 1. The second entry here should be b2 plus 4b1. So that's going to be 4 plus 4b1. That will give me 8. And the last entry should equal to 0 because this stuff equals 0. But let's just look at that. 2b1 will be minus 2 plus b2, b2 is 4, so that'll give us 2 minus 2b3, which is minus 2, which would give us 0. So this is our reduced matrix. Again, I just used this that we had already row reduced. but I just plugged in my B1, B2, and B3. I halved my R2 just to have some smaller numbers in my matrix, and I said this first column is associated with x1, the second column with x2, and the third column with x3. So I get these equations. What these equations tell me is x3 is free, and x2 is equal to 1/7, so I went ahead and divided out the 7, and then 4 minus 5x3. x1 is going to equal to 1 minus 3x2 minus 4x3. So I'm going to let, since x3 is free, again I want small numbers, I let x3 equals 1, then plugging into this equation, x2 will be equal to minus 1/7, and x1 is equal to minus 2 4/7. And this made me very unhappy because I have these fractions here, but you know, that's what I got. So anyway, x1, I plugged that in as my coefficient for my first column vector, which is 1, -4, 3. My x2 is minus 1/7 times my column vector 3, 2, minus 2. And last, I have x3 is equal to 1 times my last column vector 4, -6, 7. And lo and behold, after struggling with my fractions and adding and multiplying, I get 1, 4, 1, which is exactly B. So this is how you would get the linear combination. So what we have found, in particular, to summarize, we have this equation, and the question was, is the equation consistent? Do we have solution for all B? And in the previous slide we said no, because B has to satisfy this condition. And we could have stopped there. That would have been a sufficient answer for this question. But I went ahead and I said, well, let's just illustrate when B does follow this form, when B satisfy this condition, we really can write B as a linear combination or as equal to A times X. And I found what the X would be equal to, which is minus 2 4/7, minus 1/7, and 1. So this is our X times our matrix will give us 1, 4, 1, our B. So we've looked at this statement that the equation AXB has solution if and only if B is a linear combination of the columns of A, and we'll move on to this theorem that says let A be any M by N matrix, then the following statements are logically equivalent. And by logically equivalent, we mean that is for particular matrix A, they are either all true or they are all false. The first statement, for each B and Rm, so any B that you can come up with, the equation AX equals B has solution if and only if each B and Rm is a linear combination of the columns of A. That's exactly the statement here. The second one, that's if and only if the columns of A span Rm, if and only if A has a pivot position in every row. So we'll look at the proof of this. And what we are going to do is this circular proof. We have 4 statements, 1, 2, 3, and 4. We're going to prove that 1 implies 2, which implies 3, which implies 4, which then implies 1. So we have this circular thing. So if we want to know 3 implies 2, we could go about this circle, we're saying, well, 3 implies 4, which implies 1, which implies 2, which implies 3. So basically the circle will give us the equivalent. So we'll start with 1 implies 2. So 1, we're given for every B and Rm, the equation AX equals B has solution. That's our given, and we want to prove 2. And actually this is almost just using the definitions. So let's let A equal the matrix with columns A1, A2 to AN. Then A times X by our definition of our matrix vector multiplication is equal to the linear combination A1, the vector A1 times X1, plus the vector A2 times X2, plus up to the vector AN times XN. Again, that's just using our definition of matrix vector multiplication. So we are given that AX equals B has solution, so I put that as given. Then we know that B is equal to AX, which is equal to this linear combination A1, X1 plus A2, X2 up to AN, XN. So that means B is a linear combination of our vectors A1, A2, and AN. And just to summarize this proof, it really only used the definition, our definition of matrix vector multiplication. It used the fact that we were given AX equals B, and then finally the definition of linear combination. the second part, we're going to prove 2 equals 3. So we're going to be given 2, which is for every B in Rm, B is a linear combination of the columns of A, and we want to prove the columns of A span Rm. I am going to rewrite A, my matrix A, as several column vectors, A1, A2, up to Am. Then B, since it's a linear combination of the columns of A, is equal to A1 x1 plus A2 x2 plus AN xn. Again, that's using our given and also the definition of linear combination. Since the span of A1, A2 up to AN is equal all vectors of the form A1 x1 plus A2 x2 up to AN xn, that's just from the definition of span, what we have for every B in Rm, B is in the span because B can be written in this form of a linear combination. And that's the end of our proof. And just to summarize, we didn't use much more than the definition of linear combination and definition of span, and also our given that B was indeed a linear combination. The fact that this proof is so quick and easy shouldn't come as a surprise, since literally the definition of span is literally in terms of the linear combination. Next, we'll do 3 implies. Actually, you know what I realized? It's easier to prove. The fourth one is kind of difficult, so I'm going to prove 3 implies 1, and then later I'll come back and I'll show that 4 and 1 are equivalent. So I'm going to kind of make a circle between 1, 2, and 3, and then show 1 and 4 are equivalent. So let's do 3 implies 1. So we're given the columns of A span Rm, and we want to show 1, that AXB has solution for all B in Rm. So if B is an Rm and the columns of A span Rm, that means B is in the span of the columns of A, which means B can be written as a linear combination of the column vectors of A. That just comes from the definition of span. So then that means B can be written as a linear combination, though. So this is the vector form of our equation, but we can convert this to the matrix form, where we take A1, A2, and AN and get the matrix A times X equals B. So this is the matrix form, and if this has solution, which we said it does because it's in the span of A, then our matrix equation, by our theorem here, must also have a solution. So we have proven 3 implies 1. So what we've shown is 3 implies 1. So the column of vectors of A span Rm, then AX equals B has solution. So far we have shown 1 implies 2, which implies 3, which implies 1. So we have this circle here. So now we're going to show that 1 and 4 are equivalent. So we'll show when 1 is true, 4 is true. When 1 is false, 4 is false. We are going to start by saying let U be the echelon form of A. So given a B in Rm, we can row reduce the augmented matrix AB to an augmented matrix UD. And we'll start by showing that if 1 is true, that 4 is true. In other words, if A has pivot position in every row, then for each B in Rm, the equation AXB has solution. So let's just review what a pivot position is. In a matrix A, again, this is not the augmented matrix, but just the matrix of coefficient, is a location in A that corresponds to a leading 1 in a row-reduced echelon form. So here I have a matrix which actually isn't row-reduced, because to be row-reduced, I'd have to make this 0 and these 2 entries 0. But I can do that. Let's just, we've gone through this row reduction, so we can do that. But you'll know that these positions, the 1, 1, 1 here, will remain. So in this example, we have 3 pivots. And also, it does not meet this criteria that A has a pivot position in every row. It only has a pivot position in row 1, 2, and 3. It's missing a pivot. It's missing a leading 1 in the 4th row. So if A does have a pivot position in every row, then there is no pivot in the augmented column. Remember, this is the augmented column, and for pivot positions, we're only looking at matrix A. So if this matrix had a pivot in every row, it would also need to have a pivot in this last column. And so there'd be no, since the pivot is the leading one, the first one in the row, that means that B cannot have a pivot. Now that we know that A has a pivot in every row and there's no pivot in the augmented column, we can use this theorem from our chapter on echelon form matrices, which said a linear system is consistent if and only if the echelon form of the augmented matrix has no row of the form 0, 0, 0, B. And just to note, if you had this form 0, 0, B, then this B could become a pivot. This would become a pivot point, this B here. But we assume that there's no pivot. There's not a pivot in our augmented column. That was this point here. So that means we have no column of this form. And by this theorem that says then the linear system is consistent. In other words, AX equals B has a solution. Okay, so now we've shown when 1 is true, 4 is true. So next we want to show they're equivalent, we want to show when 1 is false, 4 is false. Now to show the other equivalence, when 4 is false, that 1 is false. So we're going to start by assuming that A does not have a pivot in every row. So A does not have a pivot position in every row. That will have to mean the last row is all zeros. And then let D be any vector with 1 in its last. So you can choose, remember D is our augmented matrix, and you can choose B. So by the time you row reduce, you still get some number. Let's just assume it's 1 in the last entry. Then we know that this is inconsistent because we have x1, x2, x3, x4. 0 x4 is equal to 1, and there's no x4 that can satisfy this condition. Thus, our AX equals B is inconsistent. Now that we've talked about existence of solution, we can come to a more efficient way of computing AX. The way that we've been doing it so far is a really good conceptual way of seeing the connection with the linear combinations. But next we're going to look at, which essentially is matrix multiplication. And the way we're going to define this, if we have A times X, a matrix times a vector, then the ith entry in AX is the sum of the products of the corresponding entries from the ith row of A and from the vector, the ith element of X. So in other words, if A is equal to 2 minus 1, 6, 3, 5, negative 2, 4, negative 3, 8, and X is equal to x1, x2, x3, then what we can do, and I'm just going to do this using our linear combination formula from before, we take this first column is associated with x1. So we're going to multiply our first column times x1. Our second column is multiplied by x2, and our third column is multiplied by x3. So doing our scalar vector multiplication, we get 2x1 minus x1, 6x1 here. We get 3x2, 5x2, and minus 2x2, which is here. And then we have 4x3 minus 3x3 and 8x3, which is here. Now we can do our vector addition, and we get 2x1 plus 3x2 plus 4x3 for our first row. And then we have minus x1, 5x2 minus 3x3 for our second row, and 6x1 minus 2x2, 8x3 for our third row. So what we can do is look at this, and we can say essentially what we've done is we can take the first row that for the ith entry. So for the first entry in A times X, we can take the ith row, that's the first row, and multiply by X. So we're going to take 2, 3, 4 and multiply x1, x2, x3, sort of like a dot product. 2x1 plus 3x2 plus 4x3. For the second entry in AX, we're going to take the second row multiplied by x. So that's minus x1, 5x3, 3x3. And then for our third entry, we're going to take the third row times x, which is 6x1 minus 2x2 and 8x3. So this will give us our 3 rows. Also, if you're used to doing matrix multiplication, this is just matrix multiplication. Last, we have some properties of the matrix vector product A times X. So if A is an M by N matrix and U and V are vectors, and c is a scalar, then a times u plus v is the sum of au plus av. And a times a scalar c times u, you can pull out the scalar and multiply that times au. I moved my theorem here, and then I'm going to prove for n equals 3 for R3. So for R equals 4, R equals 5, the proof would be similar. So I'm going to first write A as the column vectors A1, A2, A3. U will be the vector U1, U2, U3, and V will be the vector V1, V2, V3. And the reason why I wrote this as column vectors is because we have properties of our vector of Rn, of our vector addition, vector multiplied with this scalar. So I'm going to use those properties from Rn. So if I look at AU plus V, and I want to prove that's equal to AU plus AV. So AU plus V. So I'm going to write A as my column vector matrix, A1, A2, A3. U plus V then is going to be U1 plus V1, U2 plus V2, U3 plus V3. So this is my matrix equation. And I can transform that to my vector equation then. So that's going to be A1 times, and this is just a scalar, U1 plus V1 is just a scalar, U1 plus V1. A2 times the scalar, U2 plus V2, and A3 times the scalar, U3 plus V3. And remember, there's a logical equivalence. They have the same solutions. So I can do this. Then what I can do then, why did I write this here? I guess I was just saying that there's this vector equation and matrix equation have an equivalence. They have the same solution. I think that's the only reason why I wrote this here. So here I have my vector equation, but now I have from our algebraic properties of Rn that I can, when I have a vector times a scalar plus a scalar, I can make that the sum of the vector times the first scalar plus the vector times the second scalar. So I do that also for this second term and this third term. And again, I'm using now properties of vectors. Oh, and I wrote that down here. This was from a previous video when we talked about vectors in Rn. This is the property we are using here, where we have two scalars multiplied by a vector. We can separate this out. So that's exactly this property here. Now next, using these two properties, one, because when you have a vector plus a vector, that's commutative, and also it's associative. So here, A1 times U times a scalar is a vector. A1 times another scalar, V1, is a vector. So each of these terms is a vector. So I can move them around and I can associate them because vector addition is both associative and commutative. So I grouped all my my U terms. So I have A1 U1 plus A2 U2 plus A3 U3. So I got this term, and this term grouped together. Then I have my V terms, A1 V1 plus A2 V2 plus A3 V3. And finally, just looking at the definition of my matrix times a vector, this here is just equal to the matrix A times the vector U, and this here is equal to A times the vector V. So I have proven that AU plus V is equal to AU plus AV. Proving that A times a constant C times the vector U is equal to pulling out the C times AU, I use sort of the same strategy. I'm going to use the algebraic properties of vectors to prove, properties of the matrix. So I have A times CU. So I'm going to write A as vector columns because I have properties about vectors I've already proven. And then I'm going to write CU as CU1, CU2, and CU3. And now using my definition of how to multiply my matrix times my vector, I'm going to have CU1 times A1, CU2 times A2, and CU3 times A3. And these two are equivalent. The matrix equation is equivalent to this matrix equation is equivalent to this vector equation. And now, by algebraic properties here, if I have two scalars multiplied by a vector, I can multiply the vector by one scalar first and then by the second. So here I have two scalars, so I can group this. So I multiply u1 by a1 and leave the c out. And I did that for each of the three terms. And finally, using this property here, that once I have cu plus cv, I can take out the c. So here I can factor out the c, and I get c times u1a1 plus u2a2 plus u3a3. And then this is just equal to c, and by definition of matrix vector multiplication, this is equal to a u1. And so hence I have proven that a cu is equal to c a u. Now that we've gone over our main material, I have a few more problems to go over. The first problem is to let the matrix A equal 1, minus 3, 4, 5, 1, minus 8, minus 2, 9, minus 1, 0, minus 5, 7. The vector P is equal to 3, minus 2, 0, minus 4, and the vector B is equal to minus 7, 9, 0. It can be shown that P is a solution of the equation AX equals B. Use this fact to exhibit B as a specific linear combination of the column vectors of A. So the first thing I'm going to do, and this is not part of the problem, and I'm sorry there's like problems that I actually add on to it, but I feel like it's important. So first is the statement. It can be shown that P is a solution of AX equals B. I want to verify that. First I want to think about what does that mean? And how do I verify that? So AX, this is A, times some vector X equals B. And this X, that's the vector we're looking for. What are the numbers that make this equation true? And this is saying that P is a solution. So in other words, A times P should equal to B. That's what this statement here is, that P is a solution of AX equals B. So let's verify that is true. And I'm going to use this, how we compute AX, using that matrix multiplication way. So the product AX is defined, the ith entry in AX is the sum of the products of the corresponding entries from the ith row of A and X. So for the first row of our solution, AX will be equal to, so here's A, the first row of A times our X. So that's 1 times 3, 5 times negative 2, negative 2 times 0, and 0 times negative 4, and that will be equal to negative 7. The second row then is going to be the second row of A times our vector X. So that's minus 3 times 3, 1 times minus 2, 9 times 0, and minus 5 times minus 4. And that is equal to minus 9. Our third row then is our third row of A multiplied by X. So that's 4 times 3, minus 8 times minus 2, minus 1 times 0, and 7 times minus 4, which is equal to 0. And you can see this is exactly, the 7, 9, 0 is exactly B. So again, what we've done is just we have shown that P is a solution of A times X equals B. In other words, X is what we're looking for, and this P will satisfy this equation, AX equals B. But the question was to use this fact to exhibit B as a linear combination of column vectors of A. So we need to look at this equation, AX equals B, with P plugged in as our solution. So here we have A, we have P, and we have B, and we want to write B as a linear combination of these vectors. So I've written that out here. We want B equals minus 790 as a linear combination, a constant times the first column vector 1, minus 3, 4, plus x2, a constant, times the second column vector 5, 1, minus 8, plus x3 times minus 2, 9, 1, plus x4 times 0, negative 5, 7. And if we look at this form, and we compare that to what we have in AX, well, this here, we can write this in the vector equation form, which is 1 minus 3, 4 times 3, 5, 1 minus 8 times minus 2, minus 2, 9, 1 times 0, and 0 minus 5, 7 times negative 4. And this is exactly what we are looking for here. It's the same form, except I put the constants in front of the vectors here and the constants is after, but it doesn't really matter. So this is exactly what we're looking for. So B can be written as 1 minus 3, 4, 3, 5, 1, minus 8, minus 2, and minus 2, 9, 1 times 0, and 0 minus 5, 7 times minus 4. And remember, the 0 is okay as a weight. So this is our solution. And I did verify that this is correct. And I did that by going through taking this equation, multiplying, doing the scalar times the vector. That would be 3 times 1, which is 3. 3 times negative 3 is negative 9. 3 times 4 is 12. This minus 2 times 5 is minus 10. Minus 2 times 1 is 9, minus 2. Minus 2 times minus 8 is 16. This is 0. This is 0. Minus 4 times minus 5 is 20. Minus 4 times 7 is minus 28. And then when I add these all together, I do get my vector minus 7, 9, 0. So I have verified that these coefficients, 3, minus 2, 0, 4, do in fact give me the solution I want. But in particular, this here is the solution. And again, this was just the verification by multiplying everything out to see that it actually does work. This next problem is to let A equals 2, 3, 5, 1. The vector u is equal to 4, negative 1, and the vector v is equal to minus 3, 5. And we want to verify the theorem that says A times u plus v is equal to au plus av. In other words, do this side of the equation and verify it equals the calculations on the other side of the equation. So I start with the left-hand side of the equation. Yes, a plus u plus v. So I have a here, 2, 3, 5, 1. And then u plus v is 4 minus 3 and minus 1 plus 5. That's u plus v here. So 4 minus 3 is 1, minus 1 plus 5 is 4. And now I can do my vector equation, which is for the first row, I take the first row of my matrix multiplied by my x. So I get 2 times 1, which is here, plus 5 times 4. For my second row here, I'm going to take my second row of my matrix times my x, so 3 times 1 plus 1 times 4, and so that's going to be equal to 22, 7. I compare that to AU plus AV. So AU, again the matrix 2, 3, 5, 1, U is 4 minus 1. I'm going to multiply the first row times my matrix, so that's 2 times 4, 5 times negative 1. My second row times my x is 3 times 4 and 1 times minus 1. This ends up being 3, 11. Then AV, again my matrix A, 2, 3, 5, 1. V is equal to minus 3, 5. So I have 2 times minus 3, 5 times 5. And 3 times minus 3 plus 5 times 1, and that'll be 19 minus 5. And if I add AU plus AV together, I get 22, 7, which is the same thing as AU plus V. This last problem is to construct a 3 by 3 matrix A and vectors B and C in R3 such that AX equals B has solution, but AX equals C does not. This one is interesting, and I encourage you to try it on your own. And if you get stuck, I'll have a hint on the next slide, and then I'll encourage you again to try working with a hint. And then finally, I'll give you the solution. So pause the video and give this one a try. So my hint is to use this theorem here. So pause the video if you haven't come up with a solution, give it a try. So the thing that stands out about this problem is you do not want the matrix equation AX equal B to always have a solution. I mean, in this case, for B, you do. But when it's equal to C, you don't. So in terms of this theorem, you do not want this statement to be true. You do not want for every vector in Rm that the equation AXB has solution. Since you want this to be false, that means this last statement has to be false. That means A cannot have a pivot position in every row. So that's what's important about constructing A. So I constructed my A so there's not a pivot position in the last row. and then I constructed B and C. Well, actually, B had to be a certain way, but I constructed C so that there's a 1 in the last row. And then B, I think I just chose small numbers, but let's look at that in a minute. But yeah, I just chose some small numbers. So now when we have AX equals B, we have 1, 0, 0, 0, 1, 0, 0, 0, 0, that's A. B is equal to x1, x2, x3, which is equal to 2, 3, 1. So the solution to this equation is x3 is free, and x1 is equal to 3, x2 is equal to 3, and x1 is equal to 2. Whereas here now, when we have a 1 here, I chose the 1 because that will make this inconsistent, because we get 0x1, 0x2, and 0x3 equals 1. And there's no x3 times 0 that will equal to 1, and this is what makes my solution inconsistent. In this video, we looked at the matrix equation AX equals B. First, we talked about how to multiply a matrix times a vector. And so if we have a matrix A, we looked at the column vectors A1, A2, and AN, and we multiplied by this vector x. So that would be equal to the linear combination x1 times A1, x2 times A2, up to xn times AN. We also looked at how that this system of linear equations represented by this augmented matrix has the same solution as the corresponding vector equation, where the vector for x1 in front of x1 is equal to the coefficients in front of our x1 in the system of equations. The vector in front of x2 is the coefficients in front of x2, and the vector in front of x3 is the coefficients in front of x3. So these two will have the same solutions. And then if we convert this to a matrix equation, just taking these column vectors, putting them into a matrix, and then our vector x equals 4, 1, this matrix equation will also have the same solution as the vector equation. We talked about the existence of solutions, and we said that these 4 statements were equivalent, that if every B in Rm has a solution for Ax equals B, then that means each B in Rm is a linear combination of the column vectors of A, and the column vectors of A span Rm, and A has a pivot position in every row. We also talked about an efficient way of computing Ax. So this definition here was good for being able to see the vector equation, but we can just use our regular matrix multiplication, and eventually it becomes a quick way of doing this. And then last, we have properties of the matrix vector product Ax. One, if you add 2 vectors and then multiply by A, you can multiply each vector separately by A and then add them together. And last, if you multiply a vector by a constant and then multiply by A, you can take the constant out and multiply it by AU. So that's it for this video. Thank you for watching.